This time I want to talk about the output impedance of op-amps. Now, if you look on the datasheet of op-amps, you'll find that the output impedance is sometimes not specified. You have to either deduce it from other characteristics on the datasheet or measure it. And one reason that it is not specified is that in many applications of op-amps, particularly at low frequencies, it's really not a significant problem at all. Typical op-amps will have values of output impedance of somewhere between 10 and 100 ohms. But the reason this doesn't cause a problem is that if you have feedback around the op-amp, as most op-amps circuits do, then that is effectively reduced by a factor of the gain of the op-amp amplifier divided by the open loop gain of the op-amp. In typical cases where the gain of your op-amp circuit might be 10, and the open loop gain of your op-amp is 100,000, then that reduces the effective output impedance to negligible levels. Now we can see how that works by considering another equivalent model of an op-amp. This little triangle inside here, this is an ideal op-amp. The big triangle is our model of a real op-amp which has a finite output resistance which I've labelled R out. And we can consider what the Thevenin equivalent resistance of the output of this circuit would be by constructing a Thevenin equivalent model of it. And the argument goes like this. Firstly, consider what the open circuit output voltage will be. Well, the open circuit output voltage is the value of Vout when there is nothing connected to the output at all. So there's no current flowing out of Vout. There will be a small current flowing down through RF and R2, however. Now the op-amp, being an ideal op-amp, will be trying to maintain its two input voltages at approximately the same voltage, which it will be able to do, provided Vout is set so that the inverting input there is equal to Vin. And I can apply the potential divider equation to work out what Vout must be in terms of these two resistors and Vin, just as I would with a typical ideal op-amp. I would determine that V minus, the input there, which must be equal to Vin, is equal to Vout times R2 divided by R2 plus RF. And it's just the potential divider equation, Vout going through RF and R2. And that gives me that Vout is equal to R2 plus RF over R2 times Vin. And that is my open circuit voltage. Now, the Thevenin equivalent resistance is the ratio of the open circuit voltage to the short circuit current. And I can work out the short circuit current by saying what would the current be flowing out of my op-amp if I connect Vout to ground. Well, if I do that, then I've got 0 volts here. If I've got 0 volts here, I will have 0 volts here as well, so the inverting input to my op-amp would be at 0. That means the output of my ideal op-amp there is going to be A, the open loop gain, times the difference between its inputs, which is Vin minus 0, or just A times Vin. That would be the output of this ideal op-amp. That will produce a current flowing through R out of the voltage across R out. Well, it's A times Vin on this side and 0 on this side, so the voltage across the resistor is A times Vin. The current through the resistor is therefore AVin over R out. And that's my short circuit current. All of that current would flow out of the op-amp. My Thevenin resistance is then just the ratio of the open circuit voltage to the short circuit current. And noting that R2 plus RF over R2 is the gain of my circuit, and the fact that the Vins cancel, this just gives me G over A times R out. And that is an approximate expression for the effective output impedance of this amplifier. Much, much smaller than the actual output resistance of the op-amp. It only starts to become a problem when you get to frequencies at which the open loop gain is of comparable magnitude to the gain that you're trying to get out of the circuit. So once you get up to the 3 dB bandwidth of your op-amp amplifier, then your output resistance is beginning to increase and could be 10 ohms or somewhere around about there. But provided you're a long way below the 3 dB bandwidth of your op-amp amplifier, you don't really need to worry about R-out in any practical case. That's all for this time. Next time, I'll look at the issue of common mode rejection ratio and the effect of variations in the power supply.